Hello students, and welcome to this last video on study unit 2, digital codes and error detection. Okay, so we'll get to all those soon. So first of all, why digital codes? Well, these codes are specifically developed to make a very specific purpose. Here we'll discuss BCD, binary coded decimal, and gray code. And then finally we will come to a couple of error checking codes. But first of all, binary coded decimal, BCD. So BCD is a binary representation of the 10 decimal digits. It is often referred to as the 8421 BCD code because of the weights given to the positions of the bits. Because we like to work in decimal, this code forms an excellent interface for binary systems, which is all well and good, but how does it look like? So in this table, as you can see, for BCD we only use 4 bits to represent a number, and we can use these 4 bits to represent from 0 to 9. So it goes the same binary as you're used to, but then when you come to 10, when we have 2 decimal digits, we use a 4-bit BCD code for each of these digits. So here, this BCD code represents 10. And 11 will be 001, 0001. So once again, why would you want to do this? It just seems to make everything more complicated. Well, as I said in the beginning, it makes specific things a lot easier. Like for instance, if you're working with 7-segment displays and you want to display a very large binary number. Well, let's say we want to display the number 82. So binary of 82 is 10100010, and if we want to display this, we need 2 7-segment displays. But it is difficult to represent this number in 2 7-segment displays. Because how would you go about that? Because the 2 7-segment displays are two very different, apart entities, and they can't display such a big number on their own, but together they can, but it's just more difficult. So the easiest thing to do is to break up the decimal number 82 into 8 and 2. And then 8 and 2 is a lot easier to display on the 7-segment displays. So here we have number 82, we break it up into 8 and 2, and then 8 and 2 we break up into its binary equivalent, and that is easy to display. And then number 2 is also very easy to display on one 7-segment display. So this is the normal binary number for 82, and then this would be the BCD code for the binary number. So if you would take 82, you break it up into the binary BCD code. This makes the computation a lot easier, because now we use things like lookup table. It goes to see, oh, this is 8, and then the value for 8 is this for the 7-segment display. So you only have 10 values in this for 7-segment display. But if you use like this, then you will have 100 values for these 7-segment displays in one large table. So you have one table of 10 values which you use twice, rather than having 100 values. So gray code. And gray code is an unweighted code, which means a bit's position does not affect its value necessarily. The main property of the gray code is that only one bit changes at a time. We use this in shaft encoders, which reduces the possibility of erroneous interpretation. I'll explain that a little bit better later on. So this is the digital code. You have decimal here, and then gray code. As you can see with gray code, only one bit changes at a time. So we have binary, a lot of bits can change at the same time. But here in gray code, only one bit changes at a time. So it makes just shaft encoders just easier and makes it less likely for them to make an error. So if you just change one bit of the counter at a time, the chances of making an error by changing multiple bits is a lot less by just using gray code and changing one at a time. So now we come to converting binary to gray code. Now the most significant bit of the gray code is the same as that of the binary code, and also vice versa. And to obtain the next bit of the code, we add the adjacent pairs from left to right, discarding any carries. So here we have the binary number 10110. So the most significant bit is the same. For binary we add 1 plus 0, which is 1. So we write 1, which is the next bit. The next bit 0 plus 1, which is 1. And then for the next bit 1 plus 1, which is 1, 0, but we throw away the carry, so it's just 0. And then once again 1 plus 0 is 1. So that is the gray code. So once again, you just add the binary numbers, the adjacent binary numbers, and discard the carry. So here, most of the bits stays the same. 1 plus 0 is 1. 0 plus 1 is 1. 1 plus 1 is 0, because we throw away the carry. And then 1 plus 0 is once again. So this is the binary number, and then convert the gray code conversion beneath it. And then gray code to binary, the process is very similar. Most significant bit stays the same, and obtain the next binary bit. The most significant binary bit is added diagonally to the next gray bit, as shown below. So once again, here we have the gray code up top, and then binary. Most significant bit stays the same, and then we add diagonally, and once again throw away the carry. 1 plus 1 is 0. 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 1 is 0. So we're back to the binary that we had with the gray code of the binary. So now we have XS3 codes. XS3 code is an unweighted code that was developed to simplify certain arithmetic operations. It is obtainable by taking the decimal number, converting it to BCD, and then adding a 3 to each group. And of course, the reverse, you just subtract 3 and then take BCD decimal. So now we convert 648, decimal 648, to XS3 code. So 648, we have the binary number for 6, for 4, and for 8. And now we just add 3, like 0, 1, 1. We add 0, 1 to that, we get, and this is the XS3 codes. Now we come to alphanumeric codes. Now alphanumeric codes not only represents number, but also represents letters and special characters, especially in the ASCII. Anyone heard of the ASCII chart? So if you want to represent special characters, this is the decimal value, the hexadecimal number, the octal number. So if you input this decimal number, then you'll get 0. But if you input 74, then we'll get a J. Just make certain operations, especially if you want to have special characters in your program, just a lot easier. Now we come to error detection codes. So this is when transmitting and receiving data between 2 points. So how do we know if a reception or data packet that we received is correct? So here in this course we use parity and cyclic redundancy checks. So first, parity method error checking. Many systems use a parity bit as a means of bit error detection. Any group of bits contain either an even or an odd number of ones. A parity bit is attached to a group of bits to make the total number of ones even, and an odd parity bit makes the total odd. Given system operates with even or odd parity, but not both. So for instance, if a system operates with even parity, each group of bits received is checked to make sure that the total number of ones in that group is even. If there is an odd number of ones, an error has occurred. And the parity bit can be attached to the code either at the beginning or at the end, depending on the system's design. So we have a bit data stream. In this data stream, we add a 1 or a 0, which either makes all the sum of the number ones even or odd. So it can, and we have a so explain this a little bit further. So if we're looking for even parity, we add a bit at the start or at the end to make the sum of ones even. So here, sum of ones is 0, which we take as even. Here we have only one in the BCD, so we have to add one parity bit to make the sum even. The same here with 0, 0, 1, 0, add 1, and here we have 1, 1, so we have 0. So 1, which makes it 1, 1, 1, 1, and then here we have 1, 2, 3 1s. We have to add a 1 here to make it even. Here we have just 1, so we have to add 1, and here 1, 2, so we have 0. So from this side, we're checking for even parity. We are checking if we need to add a 1 to make the total number of 1s in the code 1. We're checking for odd parity. We have to add a 1 to make this odd. So this is already just 1, so we have to make it 0. We have 1 here, 0, and then we have a 1 here because there's only 1, 2, which is even, so we have to add a 1 to make it odd, and so it goes on. So we either check for even parity or odd parity. So here we have just an example of detecting an error. So here we have a 0, 1, 0, 1, and this is the BCD code, these 4 bits. It can be 8 bits, 16 bits, 32 bits, doesn't matter, but just one parity bit. So we're checking for even parity. So now that is even parity. So let's assume that an error occurs and one of these data bits is corrupted and it becomes a 0 less than 1. So we have now 0, 0, 1. But according to the even parity, this whole should be have whole numbers of 1s. So the downside of this is it can only detect a single error in transmission. It can't detect 2 because if both of these falls away, then it's still even. So it will only detect if there's 1 bit missing, 1 bit that's wrong. So that's why parity is good, but it can only detect a single error. So now we have cyclic redundancy check, or CRC. In CRC, a certain number of check bits, sometimes called a checksum, are appended, added to the end, that are being transmitted. The transmitted data is tested by the receiver for errors using the CRC. Not every possible error can be identified, but the CRC is much more efficient than a simple parity check. So simply put, the CRC is based on the division of 2 binary numbers. And as we know, division is simply a series of subtractions and shifts. And so to do a specific subtraction, we use a method called modulo 2 addition. It's as the same as normal binary addition, but we just discard the carry, so it's a lot easier. So here we have an example. So if we add these together, it is 0. Add these together, it's 1. 1, 0 is 1. But for modulo 2, if we add 1, 1, it's actually 1, 0. But we throw away the carry. So it's just 0. Very important. If you have a carry, ignore it, throw it away, and just keep the other part. So this is the method we have to follow. Follow all these steps. I'm not going to go through them because it's boring just reading stuff off. We'll do an example. So example, determine the transmitted CRC for the following byte of data. We call D for data and generator code G for generator code. Verify the remainder is 0. Of course, if the remainder is not 0, there's an error. So our data is 11010011. And the generator code is 1010. So first we append the data with 0. The bits equal to that of the generator code, which is 4. So we append 4 zeros to the end of the code, the data. And then we divide the data code with our generator code using modulo 2. So remember modulo 2, we have 1, 1, which is 1, 0, but we throw away the carry. 1, 0, 1, 0, 1, 1, bring down the 0, and we do that. So 1, 1 is 0, 1, 0 is 1, 1, 1 is 0, 0, 0, 0. Remember, we throw away the carry. So 1 and 1 is 0. Okay, we don't have a carry. So we do this for every single bit until there's nothing left, and then we have the remainder, which is 100. So this is just the appended data divided by the generated code. So now the remainder is 0111. 0100, which is not 0. If it was 0, we would just append 0 here, and it's fine. So now we must append this remainder to the data. So replace the 4 zeros with 0100. So now when we send the data, the receiver checks the correctness of the data by defining it by the generator code. The result must be 0. Otherwise, an error occurred somewhere in the data, and the data must be resent. So it doesn't know where the error has occurred. It just knows an error has occurred. So the data must be resent. So it just so check that everything is right. We now divide the received data by our code, and then you will see the remainder is 0. So it goes perfectly into this number, which makes sense because we added the remainder to this number. So remember, if the answer to this division is not 0, this means there was an error in transmission, and we will have to send the data again. So thank you, this was just a video on the last module of Unit 2. If you have any questions, please email me.